Hi, everyone, and welcome to the Complexity Lounge. Today, we are delighted to be joined by Professor Karl Friston, who joins us from Queen Square Institute of Neurology at University College London. Welcome, Karl.
Thank you very much for having me. So let me repeat my thanks. It's a great pleasure to be able to speak to you. And it also allows me to answer that question that I wasn't allowed to answer before the recording starts. So, on the nature of things. Yeah, it's a tongue-in-cheek title. Um, and the tongue-in-cheek aspect is that the free energy principle starts with a careful consideration of what constitutes a thing. So I often play with the phrase "a theory of everything," but what I mean is a theory of every space thing, because it's all about thingness, and sometimes articulated in terms of self as a thing, and that sort of is a nice segue into a formal account of self in relation to self-organization, self-assembly, self-organized criticality, self-information, and so on. So that's why the title is on the nature of things, but it emphasizes the fact that this is a physicist's take on natural sciences as opposed to sort of physics per se or mathematical sciences. It's this kind of um, uh, a a calculus for the natural sciences, for self-organization, largely of a biotic sort. So, one of the reasons I'm particularly pleased is to be here is, I imagine that this is your focus. It is on the complexity that is evinced by self-organization in a biological or a biotic, and possibly even personal context. Um, I'm going to. I was given no hard limits on how long I was meant to talk or answer questions, but in my experience, it's the question and answer which is the most interesting. So I'm just going to briefly rehearse some of the fundamentals of the free energy principle, very briefly and very selectively, trying to pick out those bits that you might want to talk about later. So forgive me if it's not an in-depth presentation or I don't develop various themes. I'm just really putting on the table what we could talk about and take it in whatever direction that you'd like to. Um, so let me start. I'm going to briefly rehearse the statistics of life with a special focus on Markov blankets, and it is the Markov blanket that defines thingness or selfhood in this technical sense, and in particular, showing how it gives rise to a kind of mechanics that follows on very naturally from quantum, classical, and statistical mechanics, namely Bayesian mechanics, the mechanics of sense making and inference. Um, I'm just then going to um, take a sideways jump and um, see how this formulation of self-organization plays out at different scales, and look at that from the point of view of very large scale, um, long-term kind of self-organization through the lens of things like natural selection, but right also down at very fast time scales from a more anthropomorphic point of view in terms of action selection. Um, and then finish with a sort of reflection on the different kinds of complexity that one would expect to see at different scales, and then hopefully turn it over to a more conversational exchange with you. But to set up the first part on the nature of things and self, I'm starting with this question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? And clearly, I'm not going to answer that. But what I do want to do is just to pick out the notion of a boundary and just consider that it is necessary to define carefully what that boundary is if you want to disambiguate or individuate anything from everything else or no thing, from the self from non-self. You need to be able to define what it is that constitutes self or thingness in terms of this separation. And I'm going to read that boundary as a Markov blanket, as a statistical blanket. And for those people who don't know what a Markov blanket is, I've tried to illustrate that with this little cartoon here, where if you can imagine that these cyan circles correspond to some abstract state of the universe, and the influences of one state upon another state are denoted by these little arrows, then if I were to take some internal states of something, say me, then my internal states are surrounded by my Markov blanket. And the Markov blanket is simply defined in terms of the parents, the children, and the parents of the children. And its role is to provide a kind of statistical insulation or separation between me and the rest of the universe. It also is the interface that glues me to the rest of the universe. In the sense that separation is in the sense that if I wanted to know how my states were going to evolve over time, given the rest of the universe, then I'd only need to know my blanket states. I'd only need to know these states that enshroud me or insulate me. Technically, that is expressed in terms of conditional independence, namely that the internal states are conditionally independent of the external states if I knew the blanket states. And I'm going to make a further move here. I'm going to partition the blanket states into sensory states that influence but are not influenced by internal states, and active states that influence but are not influenced by the external states. And this enables me now to build a partition of states that you could think of as a sort of dissipative structure in a Prigogine-like sense that comprise my internal states surrounded by my blanket states, namely these active and sensory states. And just put a bit of flesh on that. This is my favorite system, thing or self, the brain. So one can consider the brain, the internal states of the brain being constituted by all the dynamics and the physiology that would be necessary to specify or list what the state of my brain is at the moment. And then my active states are those things like autonomic reflexes, actuators, muscles that then influence or change external states. And these could be in my body, that could be interoceptive or extrapersonal external states that then reciprocate by causing changes in my sensory epithelia or my sensory states, all the organs I have available for registering changes or fluctuations outside, that then in turn come back and change or influence my internal states. So this construction basically just says that, to identify something, you can now think of the influence of the internal states of the self on the outside as being mediated by active states, and the reciprocal influence of outside on inside being mediated by these sensory states. And what we've induced here is a kind of circular causality, but crucially from a sort of physics of self-organization perspective, we're now in a position to talk about the organization of open systems because these internal states are open to the environment vicariously through these blanket states. What I want to do now is ask you to forget about the Markov blanket. What we're going to do is just rehearse some fundamentals of physics, and then we're going to put the Markov blanket back into play and see what special kind of mechanics emerges just by having this way of disambiguating self or thing from nothing or non-self. The physics at hand here, if you don't like the equations, please don't worry about that. They're just here to remind me how to develop this Bayesian mechanics. But we're going to start with something which all physicists start with, basically a random dynamical system. You can read this as a Langevin equation, and all it's saying is that there is some state, some abstract state of the universe that has dynamics, changes with time, that's the x dot, that can be decomposed into lawful, slow flows that are dependent upon where you are in this abstract state space. Plus, some unpredictable, fast, random fluctuations. And I've tried to describe the kind of objects that we're talking about here with this graphic here. So I've illustrated this system, say me, in terms of two states at any arbitrary scale. It could be very fast fluctuations, electrophysiological fluctuations in a brain cell. It could be cardiac phases of my heart beating. It could be me getting up in the morning and doing my emails, having a cup of coffee. At any scale, the description of my dynamics has a unique characteristic. Basically, my trajectories through this state space don't go off into infinity. They don't wander off into infinity, which has a fundamental implication that they must turn back on themselves through their itinerant orbits. They must be technically on an attracting manifold, a pullback attractor. Another way of expressing this is there must be a non-equilibrium or far from equilibrium steady state solution that simply means that I will always be found in some states that characterize the kind of thing that I am, which means that in all the ways that I could exist, there's only a small number that is confined to this characteristic or attracting set that is viable in the sense that if I wasn't in this state, I wouldn't be me, and I wouldn't be, I repeat, the kind of thing that I am. Mathematically, we can sort of pursue the implications of this very simple definition of what something is if it possesses characteristic states, technically a pullback attractor, by appealing to an equation that describes the the probability, the changes in the probability that can be used, or that one can interpret this the density of these trajectories as subtending. If I interpret now the density of these trajectories as a probability you'll find me in a particular state if sampled at random, then we know how this probability density in and of itself changes as a function of time. But I've just said I am always, or I am only interested in those systems where I keep on revisiting the same state. So the probability distribution does not change with time, which means I can take this here Fokker-Planck equation, and this is also known as a time-independent Schrodinger equation, a master equation in some fields. I can take this equation and I can set this to zero. And if I set this to zero, the rate of change of this distribution here, I get this rather remarkable result. And this is due to Helmholtz, technically a Helmholtz-Hodge decomposition. And what it says is, if I exist in the sense that I've just described, it means my dynamics, my flow through state space, can always be expressed as a gradient flow on the gradients of the log of the probability that I am in the most likely states that I occupy, given I am me. And this flow, this Helmholtz decomposition, has two parts to it. There's one hill climbing part flowing up log probability gradients to counter the effects of the random fluctuations. And indeed, this gamma scores the amplitude of these random fluctuations. And then there's another part which gives it this sort of circular solenoidal aspect that flows around the gradients. And to my mind, this is really important because it means that for the kinds of systems that this is describing, you have to have some kind of orbital, sinusoidal, or solenoidal non-dissipative dynamics, such as biorhythms, oscillations, life cycles, reproduction, replication. There has to be some circular aspect to the self-organization and to the dynamics. I just try to illustrate that with something that we'll all be familiar with, which is water flowing down a plug hole. So the gradient flow is going down in this instance, the negative potential or log probability gradients, and the circular flow is exactly this solenoidal flow that in the limit could be described in terms of motions of the heavenly bodies as they orbit around. But what about the Markov blanket? Well, everything that I've just said applies to all the subsets or all the partitions um, due to the Markov blanket. So if I possess a Markov blanket, what I've just said has to be true of my internal states and my active states. So it'll look as if, or I can describe my internal active states as doing this Helmholtz-like gradient flow on the log of the probability of my blanket states, here the sensory sector of my blanket states, given I am me. Now, notice, but by construction, the internal and active states don't depend upon the external states. So I can limit myself now just to describing my autonomous states, my internal and active states, as being driven by these probability gradients on this function here. And the story I'm going to tell is that in some sense, we can look at this as perception and action, but we'll come to that a little later. Um, you're probably all familiar with with this sort of Helmholtz decomposition read in different fields and different disciplines. I've listed a few here that I imagine many of you will have heard of or work in. So what is this quantity that it looks as if my autonomous states are trying to maximize? Well, I've just said it is the probability of being in states that are characteristic of me, that you're likely to find me in. They have value for me. They are the ones in which I am found, in which I survive. So we can associate this with value. So it looks as if perception and action are trying to maximize value. And of course, this is just a statement of reinforcement learning, or in engineering, this would be optimal control theory, and economics, it would be expected utility theory. Interestingly, the negative of this value is known as self-information in information theory, also known as surprise, or just more simply surprise. It just scores how surprising it would be to find me in this particular sensory state or state of sensory exchange with the environment. And this information theoretic reading of this quantity leads us to things like the principle of maximum mutual information, minimum redundancy, and the free energy principle, in virtue of the fact that the free energy provides a variational bound on this quantity. So you can think of free energy as just as surprise. How surprising is this state of being given the system, or me as that system? Interestingly and nicely, the average of the self-information in information theory is entropy, which means it looks as if perception and action are trying to counter increases in entropy. It looks as though they're trying to place an upper bound or minimize entropy on average over time. And of course, that's the holy grail of self-organization. In physics, say synergetics of the kind promoted by Hermann Haken. And if I was a physiologist, it would just be a statement of homeostasis. It would just mean it looks as if in self-organizing, if I possess a Markov blanket that preserves my individuation from the rest of the universe, it'll look as if I am trying to keep my essential variables, my internal states, my blanket states, within viable bounds that are characteristic of me. There's a final interpretation here that I want to leverage, which is that of a statistician. So she would say, oh, well, this is just the probability of some sensory data given me as a model of those data. And in statistics, that's known as Bayesian model evidence. So that's one way of looking at the genesis of things like the Bayesian brain hypothesis, and particular aspects of that, such as evidence accumulation and things like predictive coding, fall out of this notion that we can always interpret being, in the sense of possessing a Markov blanket, as looking as if you're perceiving and acting in a way to maximize evidence, sometimes called self-evidencing. Poetically, you could say that just being is gathering evidence for my own existence. What would this, and this, this self-organizing dynamics, is an emergent property of a very simple sort. And just to illustrate what it looks like and how elemental it can be, what we've done here, we've simulated 128 little macromolecules that are coupled both in terms of short-range electrochemical repulsive forces and attractive forces of a slightly longer range, just to see how they self-organize. And crucially, will we get a Markov blanket emerging from this self-organization? If so, how can we associate this with sort of living organisms or natural kinds that we see around us? So what I've done here, each of these little simulated macromolecules basically was equipped with dynamics based upon the Lorentz system or the Lorentz attractor. And the reason that we were doing this was that because we were able to write down the influences that were sort of short range influences, we now can go in there and identify a set of internal states, say these blue states here, and using the Jacobian that scores the coupling or the influences among these states, we can identify the parents and the children and the parents and the children, and then plot or color code those molecules to identify a little creature living in this simulated primordial soup. So the blue states now are the internal states. The active states underwrite or underlie the magenta sensory states that then are pushed into this soup, the external states around, just to illustrate how simple it is to simulate and in this particular example, simulate a little sort of viral-like particle with macromolecules with a tiny tail, and how it sort of jiggles around and lives in this non-equilibrium, far from equilibrium steady state in relation to its external milieu. And then I could go on and demonstrate that we can do experiments on that little creature. We can show that the internal states, in some sense, encode what's going on the outside. But I'm not going to do that for the sake of time. I'm just going to jump immediately to, how can you understand this description of self-organization as it applies in the real world, and in particular, how can one understand the different scales of its application and how one scale contextualizes the scale below, the scale below, and how the scale below informs and causes the emergence of dynamics at the scale above. So I'm just going to introduce the notion of the renormalization group and motivate this by asking a very simple question. Basically, what is a state? So at the moment, we sort of assume the existence of some state space, and from that, we can look at the coupling among states, and then we can get a Markov blanket, and then we get this sort of physics that can be read in various ways, ultimately self-evidencing, and the implicit Bayesian mechanics of that. But we haven't actually addressed the simple question: what is a state? And the one resolution to that is to invoke the renormalization group by a recursive application where you can build states from states at the level below. So mathematically, or no, not mathematically, but certainly in narrative form, you can say, oh, what is a state? Well, I can say a state is a mixture, in this instance, an eigenstate of a particle's Markov blanket. And why would I say that? Well, I've just said, or I have defined the Markov blanket as that which renders the inside of something conditionally independent of the outside. So what that means is everything I need to know about anything is on its surface, it's on its blanket. So if I want to summarize everything I need to know about anything, I can just take the eigenfunctions of its Markov blanket. So I can say a state is just of a particle is just the eigenstate of a particle's Markov blanket. But now I have to say, what is a particle? Well, I already defined a particle. I can say a particle is a set of blanket and internal states. And that now leads on, well, what is a state? Well, a state is now going to be the eigenstate of the particle at the next level, and so on by construction. So I'm dissolving the question of where do states come from by basically appealing to the renormalization group that I'll illustrate in a second, all the way up and all the way down, that states inherit from particles, and particles are composed of states that generate particles and so on and so forth. I won't go into this in any detail, but there's a fairly straightforward way of doing this with empirical data and in simulations that basically involves going round in circles, generating increasingly higher order aspects of a system through, first of all, throwing away the internal dynamics and just focusing on the blanket states of any particle to generate some states at the higher scale, and then partitioning them according to that Markov blanket partition in terms of parents and children, parents and children, to create then a set of new higher level particles with their internal states and their blanket states that then subtend the states at the next level, and so on and so forth. And there's some lovely maths that allows you now to see where all the fast internal fluctuations go and how you recover just the slow dynamics as you move from one scale to the next scale, in basically inducing in a self-similar fashion exactly the same kind of self-evidencing or Bayesian mechanics at each and every level. And that's what's illustrated here. It's just a mathematical way of expressing what I find very interesting is that the, the as you go from one scale to the next scale, you're basically slowing down because you are dispensing with the fast intrinsic fluctuations that characterize what's going on the inside of things that you're averaging away effectively. And furthermore, by taking the principal eigenvectors, you're again effectively eliminating or throwing away the fast things. So what that means is that at the higher scale, you're providing a context that by construction has to outlive whatever is contextualized, the content at the lower scale, and so on all the way down. But at every level, you can still interpret the system as self-organizing according to this self-evidencing interpretation. I just introduced this as one thing we could talk about, so you can apply this in evolutionary thinking. So you've got these slow Markov blankets read in terms of extended genotypes and different kinds of things that then provide the context or have a top-down causation to a faster level, which would be sort of an extended phenotype, the lifetime of a particular organism, where if you like, the initial conditions or the starting point of some fast fluctuations that show this self-evidencing at the phenotypic level are supplied by, for example, the extended phenotype or epigenetically. So we can look at, if you like, the behavior of things, the phenotype, from the point, as searching for evidence that it exists, trying to implicitly model its environment through this Bayesian mechanics or this interpretation of the Helmholtz decomposition in terms of modeling an environment and making inferences about the hidden causes behind the Markov blanket, whilst at the same time interpreting evolution as the same free energy minimizing, evidence maximizing process, but at a much slower time scale. And technically, that means you can read natural selection as a form of Bayesian model selection in exactly the same way that we were talking about self-evidencing being part of the Bayesian brain hypothesis. I'm going to conclude in a moment just by turning to another kind of selection that ensues from the self-evidencing perspective, which I think maybe another sort of starting point for discussion. Is the self-organization I've just described apt for describing you and me in terms of intentional behavior, and indeed knowing or recognizing or inferring that I am actually me, that I have a sense of agency? What you'll probably argue not so, and ask about the different kinds of things that this mechanics could describe. And from the point of view of the Markov blanket, different kinds of things emerge when you start to remove different causal influences and different coupling among this particular partition, this Markov blanket partition. And one really interesting thing is when things, say, move from a single cellular organization to being multicellular, when they acquire a hierarchical depth, things deep on the inside now become sequestered. They are no longer influenced by the blanket states, and in particular, the active states. So, what would happen if I now removed that influence of? So, I'm moving from a single cell where the actin filaments, for example, were the active states. They were part of the intracellular internal dynamics or coupled directly to the intracellular dynamics. But what would happen if I removed that influence and I wanted to describe something that's much bigger and had a deeper hierarchical, more complex structure? Well, because we can interpret the internal states as effectively modeling the causes of the sensory inputs, namely the external states, the active states now become vicariously causes of the sensory states, which means I can now read the internal states as effectively not just inferring the causes of the sensory impressions on the Markov blanket, but also my own actions. So this leads to this interesting situation where I'm acting upon the world, but I can't feel that directly. So I now have to infer, what am I doing? I have to, or I can be interpreted as accumulating evidence for what I am doing and explaining and predicting that kind of evidence in the sense of this Bayesian statistician. Um, and that calls into play the variational free energy functionals that describe not just the actual action, but my beliefs about the action. That's normally described as written down as an expected free energy. The free energy I'd expect if I was acting like this, if I was selecting this action or this policy. And I just wanted to end by unpacking the functional form of this expected free energy in relation to the free energy that effectively provides this bound on the surprisal or the self-information. Because I think the symmetry here is quite compelling. Again, if you don't like equations, please ignore this, but just focus on the narrative. What I've done here, I've written down the free energy, and I've written down the expected free energy. And I've done so in a way that different people would recognize. So the free energy in machine learning, for example, will be known as an elbow, an evidence bound. And it's called that because it's effectively the addition of a log of the evidence that we were talking about before, the Bayesian statistician's interpretation of the probability of some sensory data given me, equipped with a term that can be never less than zero, a KL divergence. So that's what makes this free energy different from the actual surprisal or self-information or negative log evidence. It's just you're equipping it with something that can never be less than zero. So if I minimize the free energy, that goes to zero, the free energy becomes the log evidence. But I can rearrange these terms and interpret this free energy in a very different way, interpret it in terms of trying to make sense of my sensory impressions. And this is the interpretation that a statistician would probably use. So what she would say is, well, this is basically a mixture of complexity and accuracy that I'm trying, which means that by minimizing my free energy, I'm trying to provide an account of my sensory exchange with the world that is as accurate but is as possible, but under complexity constraints, basically complying with Occam's principle or Laplace's principle of indifference, trying to find the simplest explanation possible that retains a degree of accuracy. And the nice thing is that when we take the expected free energy, given what we expect if I selected this action, the complexity and accuracy become risk and ambiguity, or the complexity and inaccuracy become risk and ambiguity respectively, and these two terms become intrinsic and extrinsic value. So what are these things? Well, if I ignore for the moment my prior preferences, my log evidence, the characteristic states I would value being in, that are preferred given the kind of thing that I am, a characteristic of me, I'm left with this thing, which is switches sign, and it's another divergence. And effectively, it describes our the fact that we are compelled just by existing to be effectively information seeking, that we are curious. Technically, in the visual search literature, for example, it's known as Bayesian surprise. It's just the difference between my beliefs about the causes of my sensations, these external states, given some sensory observations relative to my beliefs without those sensory observations. So it's just the mutual information between sensory consequence of some hidden causes. So it scores the sometimes known as intrinsic motivation in robotics. It scores the resolution of uncertainty or the information gain, the epistemic value or affordance of selecting this action relative to another action. Let me take a particular kind of uncertainty off the table. I'm going to assume that certain things can actually see all their proximal hidden states. So the sensory states and the external states now can effectively be treated as the same thing. And I'm just left with this, another KL divergence. In this instance, this KL divergence is just the difference between what I anticipate will happen if I do this relative to what I prefer, the outcomes that are characteristic of me. And in engineering, this is known as path integral control or KL control. And in economics, it's known as risk sensitive control. And then finally, if I take all the uncertainty away, there's no more epistemic affordances. I've resolved all resolvable uncertainty. I'm just left with the extrinsic value. And of course, this is just where we started, expected value, or if I was an economist, expected utility theory. So that's, if you like, a physicist's description of intentional behavior, motivated behavior that is motivated by the sort of preference-seeking, but also information-seeking imperatives that basically can be understood as in the service of gathering information for my model of the lived world. This is the coda I was talking about before. Just standing back and thinking about sort of the different scales to which you can apply this mechanics, to my mind, presents an interesting perspective on whether it is scale invariant or whether there is some Goldilocks regime that we occupy simply in virtue of the fact that we are dissipative structures. We have these random fluctuations. We have this gradient flow that is driven by the dissipative effect of the random fluctuations. And yet at the same time, we are very biological and we have this classical solenoidal kind of dynamic that gives us oscillations and biorhythms and all other kinds of dynamics or orbits that make us biological. And one way of thinking about this is just go right back to this Helmholtz decomposition here of this gradient flow up my preferred states or prior states that are characteristic, my pullback attractor, my attracting states, in terms of those that depend upon the amplitude of random fluctuations and those things that don't. So if I go down to very, very small scales, then because I'm throwing away the fast random fluctuations when I ascend scales and things become cooler and slow down in time, then it means that as I get smaller and smaller and smaller, then these random fluctuations or their amplitude starts to predominate, and I can ignore the solenoidal operator here. And when that goes to zero, I'm just left with this. And when I do that, I've got basically, I can rearrange this equation here and rearrange it as a time-independent Schrodinger equation, which means I've now got a description of the very small in terms of quantum mechanics. And if I now wanted to make the further move, I've got lots and lots of small little things. Um, then I can use this Helmholtz decomposition just to generate things like integral fluctuation theorems that underwrite statistical mechanics, a few canonical equations here, um, uh, expressing things in terms of expressing the amplitude of random fluctuations in terms of Boltzmann's constant and temperature. So high temperature means high amplitude random fluctuations. But let's cool things down and go to bigger and bigger things. Then we get into the world of, with Markov blankets in play, we get into the world of self-evidencing and Bayesian mechanics, the kind of self-organization that you'd find in natural sciences or natural history at least. If I went too far, then I would average away all my random fluctuations. I would just be left with the solenoidal component. And what does that look like? Well, it is just Newton's laws of motion and classical Lagrangian mechanics, and with appropriate um, functional forms, I can even do things like general relativity. But the point here is that now, if you go too far, you're now describing the universe in such a coarse-grained way, say the position of the planets. You're just describing the motion of heavenly bodies in terms of this solenoidal circular kind of n-body description of n-body dynamics of this classical sort. So that argument suggests that we do actually live in a privileged regime where we live in a dissipative world, but we also have this rather precise evidence-seeking kind of description available to us. So this is a quote from Ilya Prigogine. Only when a system behaves in a sufficiently random way may the difference between the past and the future, and therefore irreversibility, enter its description, just speaking to the fact that the system will have classical aspects that we all recognize in each other, but it's also got to be embedded in or exposed to the random fluctuations that equip it with an arrow of time, and in this instance, a thermodynamics. So it just remains for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Oh, thank you so much, Carl. That was awesome. I The math has made my head spin a bit, but it's also very hot here. So it could be that. Um, we had a couple of questions in the Q&A, but also raise your hands, please, if you'd like to ask Dr. Friston anything directly. Meanwhile, Tiani, do you have the Q&A in front of you, or do you want me to get in there?
I do have it. I'm not sure where to start. The first question is, what is reality? And I think it might have been a joke.
I
Or
think
maybe
I
it
think
wasn't.
I think we can ignore him.
Okay, yeah. And then there was something about seating and chair, sofa, sand, bed. I think that might have been, I'm not sure if that was a question, but the first one is um, from David. I don't have a last name or initial, so I'll just read it and feel free, David, to represent your question if there's additional things you'd like to say. He was curious about how these maths and the blanket relate to Robert Sapolsky's arguments in determined about everything being predetermined and questioning free will and human agency. That's the first wondering that we have. I'll pass to you.
Well, that's a nice way to start, isn't it? Yeah. So the very fact we're talking about starting this physics from random dynamical systems means that by definition, it's not predictable, it's not deterministic. So we're not talking about deterministic chaos. But even if we were talking about deterministic chaos, then there is built in an indeterminacy. So we're talking about stochastic chaos. Um, and so that means that the universe in this maths is a random variable. So there is no determinism of that kind. Um, and that when read in terms of, say, action selection in the way that I was talking about it, um, really does imply that there probably is a way of describing self-organization in terms of will and free will. Simply because you're selecting something, or you can be described as if you were selecting a particular path into the future. Technically, that can also be read as Bayesian model selection. But if you emphasize the selection word, then selection is a verb, it's doing something. So there are things that don't select. You know, if you remember, I was trying to make us draw a bright line between single-celled organisms, for example, or thermostats or viruses, where their active states, should they exist, are directly coupled to the internal states. Now, those kinds of things don't have, if you like, the capacity to plan into the future. They don't have any authentic agency, and therefore, and their paths into the future are just predetermined by the path of least action, which means they don't have to do a selection. I mean, they are selecting in the sense that the thermostat is doing what it's doing, but it's not choosing in on the basis of any inference in the way that you and I are. So I probably argue that free will survives in this. I'm not absolutely sure it's addressing the question because there may be a sort of philosophical position that I'm not aware of. So I'll come back to the questioner to see whether that's a satisfactory answer.
All right,
Okay.
thank you.
We have a couple of hands up. I think we should move to Tony right now. If you want to
Thanks, I
unmute
appreciate
yourself.
that. It rhymes with Rome. It's like tone rhymes with Rome. Thank you.
Okay, okay.
Karl, thank you very much for the presentation. I thought it was great. A couple of questions. The first one is last night I was in a discussion and a friend of mine asked if I thought that the brain is seeking states that reduce energy, but there he meant in the sense of physics. And I thought about your work and I said, as far as I would understand it, I think the brain is seeking to reduce surprise. I was just wondering if you could speak for a moment on how to sort of reconcile those two concepts. I know they're close, but he meant it in the sense of physics, and I meant it in the sense of information and surprise. Just thought that might be worth clarifying.
Yeah, and it's a great distinction to make. But I think it's quite reassuring that they do go hand in hand. So people like Richard Feynman would say that information energy are just expressions. A lot of people have said that, and I think that's certainly true here. So technically, the variational free energy we are talking about is, as you say, exactly a measure of surprise. It's purely articulated in terms of belief structures and probability distributions, um, and plays the role of effectively a potential energy in thermodynamics, so that the average, as you are minimizing your your variational free energy, as you're minimizing your surprise, you're effectively finding the the thermodynamic potential minimum, and that is usually expressed as minimizing your thermodynamic free energy. So, it's relatively simple to show that they both share the same minima. So it would be, in most instances, it would be very surprising not to see the thermodynamic and the variational free energy both go hand in hand. And in one sense, you could actually look at these two kinds of free energies as as scoring or describing the same system, but from a different perspective. And technically, it's actually quite simple to actually make the move from one to the other, and that you just express the amplitude of the random fluctuations that underwrite the uncertainty that we entertain when resolving our surprise or being surprised with Boltzmann's constant times temperature. So it's actually a very simple expression, just linking the thermodynamics to the information theoretic or informational kind of surprise. You're just introducing a constant of proportionality that happens to be Boltzmann's constant, and the temperature scores the amplitude of the random fluctuations. Does that help?
Yeah, I thought that was great. Thank you very much. I appreciate that.
Thanks for your question, Tone. Daniel's up next.
Oh, can you hear me? Hi. Hi, Professor Friston. Thank you very much for the presentation. A question I've been meaning to find an opportunity to ask you for a while is I'm an agile coach, which means I work with software teams. I think there's a few of us on the call in technology organizations, mostly in thinking about sort of self-organization and complexity as it relates to teams and organizational dynamics. And when I first found out about your work, I was like, oh, okay, so maybe there's a Markov blanket around an individual contributor, a team, a department, an organization, and there being sort of scale invariance there. I kind of just wanted to like put that to you and just check that my understanding of that roughly relates to active inference, and then the team is sort of sampling the environment in a way that keeps itself intact to keep itself together. Just kind of wanted to put that to you and see if that's me understanding it or misunderstanding it.
Oh no, I think that's a perfect understanding, and I think reflects a lot of work, not necessarily by me, but lots of people around the world who are applying the free energy principle in the form of active inference in a multi-agent context, in terms of federated inference, in terms of swarming behavior, for example, but also in terms of governance and belief sharing. At a community or organizational level. So I think that the key thing you're bringing to the table with that question is, if I put two of these self-organizing, self-evidencing things together, how would they get on? And then if I put a whole ensemble together, does the ensemble now form its own Markov blanket? And so on and so on. There's a subtle distinction between the sort of the scale that I was talking about before, where you're taking sort of averages of Markov blanket to get from one scale of description to the next one. And I think what we're talking about here, which is basically Markov blankets of Markov blankets, that equip this ecosystem or this organism or this structure with a particular kind of complexity that is probably best read as having this scale invariant but deep hierarchical structure. So I think that's what you were talking about in terms of a community or a startup having its own Markov blanket, but that Markov blanket enshrouds all the individuals that comprise that team. And of course, each individual itself is constituted by lots of different Markov blankets that define its organs, right down to cells and possibly even right down to the quantum level. So it's Markov blankets in Markov blankets in Markov blankets in Markov blankets. So people are looking at that from through many different lenses. One, and I'll just give you a couple of examples to see if that's what you were referring to. One very simple starting point here would be just to put two things so defined together, so that now the rest of the universe is another thing, like the first thing. So the external states become the internal states from the perspective of the first thing, and vice versa for the second thing. So now you've got a very simple model of dyadic interactions, parent, teacher, therapist, patient, customer, provider, or when if they're actually converged to the same generative model. First, let me qualify what I mean by generative model. In order to be surprised, you have to have a prediction of what could have been the case before you are surprised by what you're actually sensing in the moment. Which means that an important argument of the free energy functional is the generative model. And that you can think of loosely as basically my world model, my internal model. And it could be very, very simple. If I was a virus or a thermostat, it would just be that one number, the room has to be this temperature. Or it could be really, really complicated, and I can have theory of mind and have a deep understanding of my lived world. They both can be described in terms of these internal models entailed by the internal states. World models is another description. Generative models is a sort of technical probabilistic description. So if you get two things that constitute the entire universe that are talking to each other such that their Markov blankets merge and the sensory states of one thing become the active states of the other and vice versa, then something interesting happens. The free energy minimizing solution is that in which their surprise is mutually minimized, which means that they start to sing from the same hymn sheet. And if they're doing slow learning, because we haven't talked about free energy minimization, well, we have it implicitly in terms of the evolution of skill separation, but learning is also a free energy minimizing process. Then you can become mutually predictable simply by becoming more like your partner. And so as time goes on, as you find that free energy minima together, you become literally mutually predictable so you don't surprise each other. And the simplest way not to surprise each other is basically to share the same generative model, to have exactly the same language, the same common ground, such that I know what you're thinking and you know what I'm thinking, simply because I can infer that you are like me. And if you are like me, I can now use my model to infer your intentional stance, to infer what you mean in terms of sort of hermeneutics in conversation. So that has, I think, a really nice interpretation and of a sort of what we mean by vernacular in terms of common ground, and singing from the same hymn sheet. If you looked at that from the point of view of dynamical systems theory, that is mathematically the same as something called generalized synchrony or synchronization of chaos. So, and in this context, the synchronization manifold to which you both converge and then just play out on that synchronization manifold together, as opposed to wandering around in the joint space of you and me without any synchronization, then that is also the free energy minimizing solution. And then you get these orbits on the synchronization manifold. That just is the Markov blanket. It's basically how I hear you talk and how you hear me talk. Then that is a sort of a physicist's expression of self-organization to a kind of mathematical alignment that can be cast on repeat in terms of synchronization of chaos. And then you can start to put that in play in multiple groups. And then some people have written about sort of belief sharing as one aspect of this and group formation. And there's some really interesting literature on when you get lots of different kinds of things that are not quite sharing the same generative models, how do they tend to group together and how do they form in groups and out groups? Because you've got this tension with the expected free energy. You want to not surprise yourself. You don't want to listen to anything that's going to surprise you. So you're English, aren't you? So I can make jokes about Trump without offending, but perhaps I better not do that for everybody. But if you had a particular political leaning, you might choose not to listen to this kind of news channel because you'd be really surprised and offended. It's something that uncharacteristic of, it's uncharacteristic of me to hear that kind of thing. So you're going to be biased to your own kind of news channel, your own echo chambers that are consistent to minimize your surprise. And you just listen to people like you. Yet at the same time, you are also driven to respond to these epistemic affordances through the expected information gain part of the expected free energy. So you're always going to be slightly curious about what the other group are doing. And it turns out that the only stable strategy when you got lots of potential, when you got lots of an ensemble of individuals, is a 50-50 split. So otherwise, the smaller group gets absorbed into the bigger group and no one's surprised anymore. But the only way to keep more than one group alive is this really polarized 50-50 split. And I think that's lovely because that's exactly what we found with Brexit. It's what you probably have in all independence votes, whether in Montreal or in Spain or whatever, Biden versus Trump. The only sort of stable kind of heterogeneous structure where there are two or more different synchronization manifolds is this sort of very polarized thing. So there's interesting applications to voting dynamics and belief sharing there. Organizationally, and some people focus on the hierarchical aspect. That in order to be, in order to be, to have this deep hierarchical structure, in the same way that my brain has a hierarchy, in the same way that any sort of complex multicellular organism has this hierarchical organization. It's unsurprising that most sustainable organizations have a hierarchical structure. And it's interesting to look at the sort of the message passing and the exposure to different levels if you just look at an organizational structure, and the separation timescales that you get from that kind of hierarchical organization. So things slow down in terms of a belief updating at the higher levels. So you don't expect your board to meet every month, say, but your sprint cycle on your managers will be every 2 weeks, but your actual coders are going to be working every day, and so on and so forth. There's a sustainable company, for example, or institution. If it's sustainable, then that basically means that it must conform to these rules, or the other way around. Sustainable companies can be described in terms of this kind of self-evidence and under these deep hierarchically structured generative models. So you shouldn't be surprised to find that kind of organization. And just finally, I think sustainability is a really important way to look at this. So from the point of view of the free energy, the only thing that it is trying to describe are those things that endure in the sense of having a non-equilibrium steady state solution. So they are just descriptions. It is just a description of those things that by construction or definition are sustainable. They persist. So that means to persist is a necessary aspect of existence, and therefore everything else is in the service of persistence. So one way of reading that, of course, is that you can read that as sustainability. So that would mean that the objective of an institution or a startup is not necessarily to grow, it's just to persist, to sustain itself in the face of all the environmental or other pressures that that it's subject to. Is that what you were getting at?
Yeah, that was a very rich answer. Yeah, I think so. I think that's the kind of yeah, that's the sort of direction I was thinking about, and then how it relates to. And there's also elements of teams can be in conflict within an organization as well, and maybe each one has their own self-preservation at the expense of the other one, and maybe those that can maybe work within an overall organism, or so maybe that's the question, is like within one Markov blanket, you could have other uh, structurally lower down, lower order entities or things that are in conflict with each other, but the whole thing manages to keep itself together. I'm sure there's a equation that I wouldn't understand that describes that, but is there? How does that relate to the system? I'm aware I've also taken up a lot of other people's question time, but yeah, thank you.
Well, and perhaps the answer to that question will possibly address the sort of natural questions that I imagine people are asking. But I think that's a great question. So that would, I think, speak to something that we've discussed in terms of these deeply structured hierarchical systems. So, a Markov blanket is only really interesting in virtue of the fact that there are it surrounds lots of Markov blankets on the inside. So to define a hierarchy, which is a necessary attribute of these deep structures that show this sort of agentic aspect where you disconnect the peripheral Markov blanket from the inner structures, to define, to be a hierarchy, you necessarily have to have Markov blankets. So each level of a hierarchy is a Markov blanket that separates higher levels from lower levels. So if you want to talk about the cause effect structure or the contractual dependencies in any organization, then you are looking for exactly this kind of separation of the kind. Sometimes in neuroscience, this is called functional specialization or segregation. It's the fact that different parts of our brain are experts at doing different things. So you have to have this division of labor, but also there has to be functional integration between the functionally segregated parts of the brain, in the sense that you have to both inform and be informed by the level above, or the hierarchical level above. So what that means is exactly as you say, in a deep hierarchical structure, you would expect to see both a hierarchical structure, but also a division of labor within each of the hierarchical levels. And this mathematically is usually expressed in terms of a factorization, a kind of mathematical carving nature at its joints. So certain groups or certain parts of your brain or certain groups, groups in your organization will become specialized for this and that. You'll have sort of finance, you'll have product, you'll have whatever, and the pressure on that kind of factorization or carving nature at its joints at your particular level inherits from that decomposition of the free energy, or the, um, the log evidence that I spoke about in terms of complexity minus accuracy. So the best way to um, the best way to, if you like, explain what's going on behind your Markov blanket at the next level of your organization, or as the organization is more public facing or towards the outside, um, is to um, keep everything as sparse and as factored, orthogonal, and as specialized as possible in the simplest way possible. So you'll get the minimum number of specialists in play where there's no redundancy. So another way of thinking about minimizing complexity is to minimize the degrees of freedom your organization, your brain are using to explain and contend with exchanges with the outside world or the sensorium. Um, Minimizing redundancy means that there's no duplication of effort, which means that you will get exactly the kind of orthogonality or separation in terms of specialist skills within any one level of the organization. Um, um, in terms of conflict, there's always going to have to be, if you like, a resolution of the uncertainty about what's the most important, the best thing to do. So then we move on to the argument that we were talking about before about sort of action selection or Bayesian model selection based upon some criteria. And those criteria are going to be the expected information gain and the expected cost or the expected value, depending upon the outcomes. So I think that particular aspect of complexity, I suspect, speaks exactly to how you might understand the physics of self-organization in relation to hierarchical and factorized structures of message passing and accountabilities and decision making in a governmental or governance or organizational sense.
Thanks for that question and your answer too, Carl. I tried to line up somewhat chronologically from all the hands in the chat as well. So the next question would be from Rob, and that was in the Q&A. Rob, feel free if you are still here, if you are here, to chime in. And the question was, would the Penrose-Hameroff's or model of consciousness be relatable to the external state transition, internal state topology? If so, how?
I'm afraid my answer would be no. It does not. The whole point of that coda was to say that you've got to pick the right kind of scale if you want to describe systems like you and me. And if uh, you ascribe things like consciousness to things like you and me, then you've got to be at a scale that will support things like you and me, and that's not a quantum scale.
Right. Okay. All right. And the next is Ben, is it Ellers? I saw your early question in the chat, and I've seen a couple more if you'd like to ask one of those.
Yeah, basically, if it's Markov blankets within Markov blankets and going all the way down, what about going all the way up? I mean, how does all this relate to the big social issues of our time?
Right, I thought you were going to go as far as the Big Bang there, but
Well, you can do, yeah.
yeah, but I think it's quite comforting. So yeah, I mean, we touched upon this in terms of sort of polarization and population voting dynamics and the like. Um, uh, but people have taken it even further to the level of the biosphere and the Gaia hypothesis. So there are academic papers out there where you apply the free energy principle to look at dynamics and self-organization at over the millennia. And the reason it's quite encouraging is you can see certainly evidence for this kind of itinerant self-organizing dynamic simply because there are identifiable Markov blankets between things like irradiant energy and oxygen consumption in the oxygen content and the like in and biomass in the biosphere. More generically, if it's true that it is Markov blankets all the way up and all the way down, that basically means that there is hope for us that we're not going to encounter a singularity or catastrophe, certainly in the near future. Simply because for me to exist, there has to be a scale above that provides the context in which my Markov blankets can self-organize. But that is also true for the scale above and so ad infinitum, which means that at the level of the universe, there must also be this itinerant dynamic. So this is slightly counter to a view of the Big Bang and it's certainly consistent with the cyclical view of the universe. So I mean, I wouldn't take that too seriously. The free energy principle is a physics of natural self-organization that talks about the scales in which you would apply it. So I'm not claiming that you can mathematically prove that there is an orbit at a scale beyond that of the cosmos. Um, um, but I certainly think that at the level that we can reach with our telescopes and downwards with our microscopes, there it can be no other way than the context in which we operate, which we'll never see because we won't live long enough, we won't last long enough to see, say, genetic drift or to see to see these processes. We can infer it on the basis of historical data, but we won't actually be able to perceive these things. We're not around for long enough. But we do know, in virtue of the fact we are here, then that context has to exist, and that context has to conform to the same rules of existence. So if the context is a thing, then it has a Markov blanket. If it's got a Markov blanket, it must have a pullback attractor. If it's got a pullback attractor, it must look as if it's doing some kind of self-evidencing. So I find that quite comforting. Short answer to your question is, yeah, this should be applicable at any scale. And certainly, I repeat, there's a lot of interest in applying it now to geopolitics and social neuroscience and commerce and even now financial modeling. So, not that it has been to date applied in any great way, but certainly in the past 4 to 5 years, I've seen more and more papers come out along these lines.
Great, thank you. Okay, and next up, back to you, Tone.
Thank you. So one thing, Carl, that I was very interested in were your slides on scale. So we were looking across scales, and also your slide on evolution. I found that one very interesting. So one of the things that I cover in my group a lot is this evolution from hominins to humans and what is going on there. What I wanted to ask you, and apparently Brad and some others are interested in this in the chat, is something in some sense new coming into the world when you start to get cumulative culture, the kind of culture that humans have? Is this a new kind of Markov blanket that comes into the world such that the genotype, which expresses the phenotype, now has a new blanket around itself. And in some sense, we're just nodes in that blanket. Is that why we're different, maybe?
Yeah, that's a great question. And and it brings to the fore something which was implicit in that discussion of evolution or application to theoretical biology. Markov blankets come and go, and they only have a natural time life or scale that is apt for the particular scale that you're talking about. Um, and anything that is contained within your Markov blankets at a smaller time scale will come and go with increasing frequency. So, for example, some of my brain cells, some of the specializations on my brain cells that are responsible for sort of communicating between different brain cells come and go, um, you know, with a time scale of seconds to minutes. Some of my cells in my body just come and go. They only live, well, certainly my certain cellular processes only live for a matter of weeks. I only live for a matter of decades to centuries. The point being here, as you increase the scale of inquiry, you live longer, so you're providing a context for things that come and go at the level below. So, from the point of view of the level below, there is certainly novelty being generated all the time because, from the point of view of something pursuing an orbit at the lower level, it's never been there before. So it's always generating novelty, being in a new place, and then returns to the neighbourhood of. But strictly speaking, you can't tread in the same river twice. So you're always generating novelty at each scale, including the evolutionary scale. Um, and then, what I'm trying to emphasize is that a Markov blanket's not for life. Yeah, they come and go. They're very friable. So this math only applies for the duration of for the duration that the Markov blanket exists, and that could be incredibly transient. But they come and go in a context, and that context itself has a Markov blanket, and so on again all the way up. Um, so on that view, there is an inherent friability. Um, and obviously, I've wandered my stream of consciousness is forget what your question was. What were you trying to? What was the key question you were?
Oh yeah, sure. It was a great explanation. So the key question was getting at this cumulative culture, right? So sometimes Tomasello would call it the
Yeah,
ratchet. Is that
yeah.
a new
That's
kind of
so.
Markov blanket that we live in?
Yes, I had wandered so far away from your original question. My greatest apologies, but shows you what a good question it was. Yeah. So when I was talking before about singing from the same hymn sheet, and sort of dancing together on a synchronization manifold, I had exactly in mind Tomasello's common ground. Um, and furthermore, the way implicit in your question is the what is the genesis of that common ground? And I guess you're probably much more of an expert than I am. One is going to say that it can only emerge in terms of niche construction and cultural niche construction that must entail some kind of communication or language at some point. Is that in and of itself a free energy minimizing process? There are simulations that suggest yes, it is, in the sense that if I can read self-evidencing as building models in my brain that provide a accurate yet simple account of what's going on, um, then I am going to necessarily, when exposed to a universe that is constituted by things like me, so I'm in a community, my universe now has to include my generative model of that world outside has to include you. But I know that you have a generative model of me. So now there's a sophistications arm race in building the apt generative models that maintain an accurate account of the world or make accurate predictions as simply as possible. So what will happen is that my model will get more and more complex because it's now trying to predict a more and more complex model, which is you. So you get a complexity arms race simply because there are lots of things, there are lots of us. This shouldn't happen in isolation. So if I put you on Mars, then you shouldn't be subject to this. But just because we're all modeling each other, there now becomes this complexity arms race that is just a natural part of self-evidencing. So I think, from one particular viewpoint, and of course from the viewpoint of sort of recent evolution, we're just looking at sort of one fluctuation and at this grand evolutionary scale that looks as if there's a progressive complexification. In principle, it should actually it should actually return to in this itinerant way, an equivalent part of a state space at the higher level. But I think the key point you're wanting to tease out here is that this process of evolving that entails this complexity arms race is almost an inevitable property of working together and co-constructing things together. So people sometimes write about this in terms of cultural niche construction. You can also simulate this in terms of belief sharing and federated inference. That if I can, if we share not just common ground in the Tomasello sense, but actually literally we share the same environment, the same eco niche, but we see different parts of it, then if we share the same generative model, but we're both looking at different parts of our shared eco niche at different times, then I can greatly increase the efficiency of my modeling of that world if I can have access to your beliefs about what cause your sensations, your part of this shared eco niche, and vice versa. But to do that, there has to be a way of belief sharing between the two people, between the two or more people in question. So how can you do that? Well, you could do it through, if you're a computer scientist, you could do it through just sort of wiring computers up, telepathy. But for things like you and me that have a biological kind of Markov blanket, we have to do that through communication. And that can be sort of, through the spoken word, or it could be transgeneration through sort of evolutionary evolutionary psychology and co-evolution and books and memes in its original sense. Is that what you were getting at?
That's largely what I was getting at. It's just more the idea of like expanding the Markov blanket from oneself out into a group, and then that blanket, in some sense, being self-sustaining while the individuals underneath can change. And that maybe seems to be different about the way that we create artifacts, both physical and abstract. And maybe that's why we're different than so many other animals. But thank you very much for that. I appreciate it.
All right, thank you so much. All right, next up, Sandra, have your question in the Q&A. Let's say the Markov blanket describes a small startup organization. How would you describe innovation within this framework, or is this relevant? If you'd like to add anything, Sandra, to that, but that was the next question.
I don't need to add anything. I'm
All right. All right, thank you.
So innovation, I think, falls neatly under this rubric. If you think of this description of self-evidencing as resolving uncertainty. So if we just go back to the sort of the imperatives for our action selection being a mixture of information seeking and goal seeking, where the goal is to end up in my preferred states, in my characteristic states. What that basically means is to exist is to be a curious creature. Strictly speaking, a curious creature that does not expose itself to um, very uncharacteristic or surprising outcomes. Um, that basically means that anything that exists in this agentic sense, in the sense that you're actually doing this panning as inference and you're selecting actions to minimize the expected free energy, that makes you into a little scientist. Um, it makes you into a little scientist, in an explicit and simple sense that you are constantly um, interrogating the world in order to solicit those kinds of feedback or data or outcomes that are going to resolve your uncertainty about your hypotheses or your models of how your world works. And I mean this, in a very straightforward way. And my favorite example is, as all of us, as extremely skilled little scientists at many, many different levels, is the way we use our eyes. So all of us, apart from those who've got their eyes shut, are currently saccading around to every 250 milliseconds, 4 times a second. You are sampling the world simply because you only have a very um, small foveal representation of very, very high precision visual information. So you actually have to sample and then knit together on the inside through this inverting these deep generative models, finding the best explanation, inference to the best explanation as part of this self-evidencing, on the basis of lots of little punctate samples that you go and gather every um, every 250 milliseconds. But you have to choose really carefully where to look. So if you just looked at random, you wouldn't be able to sample the right kind of information that's going to resolve your uncertainty about what's causing my sensory impressions. So, if I see some unpredicted flickering in the periphery of my vision, I'm going to look over there because that's going to resolve uncertainty about what caused that. Was that a bird, or was it an insect, or was it a leaf, or a person? So I'm going to have to choose to do that. So that would be one instance of just being a scientist or complying with this um, compulsion, this mandate to be curious and specifically to act in a way that makes the world or the universe reveal itself in a way that minimizes your uncertainty about the world. At the other end of the scale, of course, you get people who are actually paid scientists who actually design experiments and can sometimes take years to actually look in the right place by designing their experiment. But they're doing exactly the same thing. They're just trying to query the world in a way to reveal scientific data that enables them to resolve as much uncertainty as they can about their hypotheses. So now, if I were to read your question about innovation as effectively, how can I be an innovative scientist? Well, first of all, I have to be able to define my hypothesis space. I have to ask the right questions before I can decide what to do in order to gather the data that's going to resolve my uncertainty about which of my questions or hypotheses are correct. So the innovative aspect, I think, is absolutely crucial for sort of higher order life forms, and it speaks to one of three sort of ways of carving up the self-evidencing, and I'll just briefly mention what they are, so I can just situate why I'm responding this way. If you're doing self-evidence very, very quickly, that's usually understood as inference. It's inference is the best explanation about what's causing my sensory input at the present time. At a slightly slower time scale, or perhaps a very much slower time scale, that's known as learning. That basically means I'm not inferring what's going on in the moment. I'm trying to accumulate and install in my generative model all those laws and contingencies, such as connection weights in a neural network or connection strengths in a neuronal network or a brain network. I'm going to slowly accumulate these things. So you've got inference and learning, and then the next one up is selection. I have to not just learn the parameters of my generative model, I actually have to select the best structure in and of itself. How many hierarchical levels? How many factors? How many sort of specialized groups do I need? So the structure, and this is something that's called the problem of structure learning in the neurosciences and in machine learning, now, also called causal discovery machine learning. In statistics, it's also known as Bayesian model selection, which is why I use the selection word, selecting the right structure. But of course, to select the right structure, you have to have a repertoire of things to select among, which brings us back to the innovative scientist who asks the right questions, questions no one has ever asked before. These are the hypotheses that mark an innovative scientist from somebody else. You could also say these are the hypotheses that marks a creative artist from somebody else. Doing something, building something, realizing something that has never been done before as a hypothesis that this is going to be the kind of thing that I, as an artist, create. Which means that you're looking now for a mechanism or a part of self-organization that allows you to build hypotheses of an innovative sort that are going to be apt explanations for your co-constructed world. And I think that that's what marks us out as distinct from the think from say bacteria or sort of lower life forms. And it's a really interesting problem practically in industry as well. A lot of people are sort of focusing on that structure learning problem at the moment. And if you just look at the benchmarks that the machine learning community are currently focusing on, they're always about this innovative aspect. So things like the Arc 3 challenge, it's all about abstract reasoning. So people are bored now with sort of showing you can play Atari games or showing that you can sort of solve maths Olympiads. What they want is sort of artificial intelligence that has this innovative aspect of being able to select de novo new hypotheses, abstract reasoning in the way that we find so easy. We're so fluent at, but other artifacts find extremely difficult. Well, it's difficult to simulate in artifacts.
Thank you.
Thank you.
All right. Next up, thank you for the hands that have been up for a little while. Murad, I think you're next.
Hi. Can you hear me?
Yes.
Great. My camera will go in and out, so apologize for that. I don't know what's wrong with it. I might need, I've been trying to formulate this question. I might need to wander a little bit to land on my point. But so this is about the thinginess. And what I gather was the Markov blanket is offered to be to explain the structure of thinginess, what a thing is and what is a thing. And so I've been thinking about the simulation of macromolecules that was presented earlier, where you had a number of macromolecules with proposed interactions between them that are distance dependent. And then after you simulate the system dynamically for a while, you start to see an organization by which I surmise the system will migrate towards a minimum potential energy arrangements, where you could see that the molecules arrange in a certain manner that allows you to label these molecules as intrinsic state, active state, sensory states, extrinsic states, and so forth. And the suggestion that I got from that presentation is that so this you can translate that into a Markov blanket, and then the idea I think was that this classification allows us to recognize a thing that's self-organized based on many components with defined interactions, influence diagrams, the influence arrows between them. And then you could see that a thing emerged out of these components that had these interactions defined between them. Now, the question is, if you look at, so the nature of the simulation, every macromolecule is offering an interaction with every other macromolecule. And look at the specifics of the equations, how these interactions were set up, but assuming that these are pairwise interactions that are universal, that every two of these macromolecules are, in fact, have a force that plays between them. But to get from the picture and the final state with the minimal energy to a definition of a thing that's self-organized, it seems to me this arrangement does not give you a crisp definition of what these states are or what is the thing, the boundaries of the thing that emerged as a result. There's some arbitrary threshold or thresholds that still have to be selected to be able to draw the various colors, designate the various colors of the various macromolecules. In other words, it seems that based on this example, the Markov blanket does not, in fact, allow you to crisply and unambiguously define the boundary between the thing and its external environment. So I was wondering, what do you think? Am I in the right realm? Is there qualifiers that actually you can add to this?
Yeah. Yeah, I certainly think you're in the right realm, and I think your final use of the word qualifies is an excellent one. So I think two important. I wouldn't. I'm not sure that I would replace ambiguous with non-unique. I think that's probably mathematically the more important qualification. But there is another qualification which we touched upon earlier on, and you implicitly refer to in terms of you have to make some sort of thresholding or put some boundary conditions on the definition of a Markov blanket, and one of the key ones again is the time scale.
It's 19.
So the times, so if you look at the dynamics that are necessary in order to what's called do Markov blanket discovery for too long, then you may have waited too long, by which time the Markov blanket may have dissipated, the thing may have died. So you have to choose the time scale and the onset and the offset quite carefully in relation to the longevity of the kind of thing you want to describe. So that's certainly an important qualification. When we're not assuming, when no one's assuming in these formulations that there is the system actually attains a non-equilibrium steady state or is agonic in any strict sense. We're assuming that for a limited period of time, then the dynamics are such that they can be described in terms of conditional independence that give rise to conditional independences that are conserved over the time scale or time window in question. So that's one really important observation and speaks to something we were talking about earlier on about the fragility of Markov blankets and their transience. So I think that's important to realize. The second, probably more important qualification, which is I think was implicit in the way that you framed your question, was that there's no unique Markov blanket. There could be many different ways of carving up that simulation, for example, and therefore there is no unique Markov blanket, and indeed one could intuit that through our discussions of Markov blankets, or Markov blankets surrounding Markov blankets. There are lots and lots of ways of carving up, carving this particular nature at its joints. So that's not to say that that there are an uncountable or infinite number of Markov blankets. There are certainly algorithms out there that I repeat, are known as Markov blanket discovery, the work of people like Jeff Peck and Maxwell Ramstead. So there are identifiable Markov blankets, but they're not unique. And that is important to understand. However, having said that, the fact that you do get the emergence of Markov blankets, um, and I have to say it is of a mathematically crisp sort. Given those two qualifications, there is an unambiguous definition of what the Markov blanket is with those qualifications. One thing which struck me by your question was the importance of noting that with certain exchangeability assumptions, that all the macromolecules, for example, in that synthetic soup, have the opportunity to influence each other in some symmetric way. Whilst that is true, there is actually at hand a really important sparsity structure that lends itself to the emergence of Markov blankets. If you remember, the Markov blanket is a way of identifying or disambiguating things, and it all rests upon the absence of causal influences, very much in the same way that a sculpture depends upon the stone that is carved away. So the sparser you get, the more likely you are. In fact, one of my colleagues has proved with probability one for a large enough system, you will with probability one get a Markov blanket, but that probability is vastly accelerated if you're dealing with a sparse connectivity. And indeed, one illustration of that was when I made the Markov blanket influence diagram sparser by removing the influence from the active states to the internal states. The point I want to get to is that in certain universes, there's a vast amount of sparsity simply because of the locality of interactions. So the way that I describe that simulation, for example, I emphasize short and long range interactions, which means that just a physical separation in some metric space precludes an influence. So if I was to write down a big matrix of coupling or an adjacency matrix for the universe, for these kinds of universe where interactions and cause-effect structures are just local, say if I was deaf and blind, then my world would really depend upon touch, and I wouldn't have this sort of action at a distance cause ability to be influenced by things that were a long way away from me. So if I was a lower life form that could only be influenced by things that were physically in juxtaposition, I've now got a universe where that adjacency matrix is incredibly sparse because I've just got entries of influence along the leading diagonal. So of all the possible interactions that could happen, there are a small, incredibly small fraction of things that are going on. And that's the kind of sparsity that simulated soup rests upon. And the simulated soup was deliberately chosen for origin of life stories, that you need that kind of high energy but localized interactions in order to get the right sparsity in order to allow these things to emerge. So while it is certainly true that there is a potential, if I took this macromolecule from over there and put it here, it could interact with me. The more important point is that I can only interact locally. And this leads to a particular kind of Markov blanket where almost paradoxically the active states are always on the inside. So if you remember, and it's a really interesting game to play. There's like a sort of mental jigsaw trying to satisfy the Markov blanket condition with different kinds of sparse connectivity structures. But the simplest one that is apt for lattices and sort of soups and microbes and single cell organisms is one in which the way that you preclude the connection or the influence of the external states on the active states is to make them hide behind the sensory states. And that's nice because the sensory states are then not influenced by the internal states because they're hiding behind the active states. So what you get from this is the sensory states are on the outside and the active states are on the inside. And then the internal states are suitably shielded from the external states. But crucially, you've also satisfied the Markov blanket. And that's very similar to the way that sort of cells are organized. But that doesn't work for things like you and me. Our active states now, well, you could argue that our muscles actually are on the inside of our skin, so you could argue that. But once you start to get things like sort of vision and hearing in play, where you violate this action at violate this locality structure, you get much more interesting Markov blanket structures with this deep hierarchical structure, and suddenly, you know. Our sensory organs, for example, our eyes, are not quite as exposed as they are in the sensory receptors, say, on a cell surface. I'm wittering, but it was a really great question.
Thank you. I mean, just to follow up really quickly, while locality of interaction simplifies things and simplifies crisps the logical structure of your argument, it's not a realistic necessarily, or let's call it, it's not an accurate reflection of what actually happens in the world, right? So in your simulation, to pre to propose conditional independence, you had to pick. So even at the very initial stage of defining what the Markov blanket is, to get to that Bayesian network, if you like, you had to pick a threshold whereby the interaction of certain molecules with certain other molecules is deemed to be insignificant and zeroed out. But even after you get to that Markov blanket, to move from that to defining the various the roles that each molecule plays within this formulation, whether it's intrinsic, extrinsic, and so forth, that is yet another semi-arbitrary, not arbitrary, but semi subjective decision that had to be made based on judgment rather than based on a calculation, I think. So the reason I'm asking this is that the contrast between the, if you like, contrived nature of that structure versus what, in our experience, very crisp and unambiguous identification of things. We're usually fairly comfortable uh, uh, distinguishing things from each other. If you follow that model, you find yourself having to calibrate it with parameters without really a clear guidance as what are the calibrated parameters should be to get an equivalent experience.
Yes, no, you're absolutely right. That you will have to make choices when simulating that very, very simple kind of emergence of a Markov blanket. So um, again, I think it's speaking to the non-uniqueness, and you'll have to identify the internal states before you can identify the blanket states. Once you've identified the internal states, everything else just follows in a crisper mathematical way. But practically the identification of the internal states is usually based upon dense mutual interactions. So literally, they're taking the sort of principal eigenfunction of usually a sort of Laplacian transform of the adjacency. But that is not unique. You could choose any one of them, and even if you then go on and sort of coarse grain or then partition the rest of some universe, where you start will very sensibly determine the final result. That's certainly true. And and it may be useful. Well, just one I'm not claiming that that was a good simulation or a model of Markov blankets that define things like you and me. I was just trying to show that these things can emerge from the simulation of random dynamical systems. I think in their application to things like you and me, then you would just read the Markov blanket. In a systems theoretic sense. So the sensitive states were just the inputs and the um, active states were just the outputs. So all you're saying is that for to be a thing in a systems theoretic sense, to be a system, just means that I have to be separable from everything else in terms of a careful and description of the inputs and the outputs. And the Markov blanket construction just says that basically to be an output, I cannot depend upon the thing that I'm outputting to, and to be an input cannot depend upon the thing that it is inputting to. Otherwise, you basically destroy the conditional dependencies. There's no statistical way of discriminating between the sender and the receiver, as it were. So I think at that level, I mean, that's where people actually use a Markov blanket. They sort of start off with a Markov blanket and then build machines and simulators on the understanding that um, you can assume the existence of a particular Markov blanket in terms of inputs and outputs, again, in a systems theoretic way.
Thank you very much for help.
Thank you so much. Okay. Next up, we have Peter. You've been so patient with your hand up for a while.
Thanks very much. Yeah, super fascinating. I would say that one of the most potent drivers of social change and innovation currently are these modern artificial intelligence systems, neural network based, which you alluded to a little while ago. And I just recently found out that you are developing a system that you think might be more powerful than some of the others. And some of the systems differ, by what training data, large language models versus maybe, I think what are called world models with more direct, maybe visual information from the world as training data. And then others, different methods of training, reinforcement learning, and et cetera. Could you give a little synopsis of what your system, how that is differs? Is it updating? Is it, versus data? And yeah, I'm really interested in that.
Right. So yeah, I mean that's an enormous, enormous field you've just uh, um, it brought into the arena of discussion. So yeah, I mean, I am not developing a system. I'm an academic who tries to deploy theoretical neurobiology and this kind of maths to understand how the brain works, and sometimes apply it in the context of computational psychiatry. But I do have lots of colleagues who work in robotics and in industry that are committed to applying the principles in this is of active inference. So application of the free energy principle to artifacts and to people usually comes under the heading of active inference. And therefore I can read your question as what's the difference between active inference and reinforcement learning? Well, there are two fundamental differences because they're baked on the tin into the labels. One's about inference and one's about learning. So machine learning, large language models included, transformer architectures and the like. These are beautiful bits of engineering, and they've been engineered to learn. What have they learned to do? To predict language or to predict drawing or coding. Um, so that means they're not actually inferring. They're not situationally aware, but they're becoming extremely skilled and expert in learning to generate. You could argue that you can learn to infer. That's certainly one application of this kind of technology. It's known as amortization, where you learn to infer something. But the problem with that is that you can't learn to be curious. And if you come back to our earlier conversation, one of the tenets of the free energy principle and its applications in things like active inference is that you need to equip self-organization of any kind with this information seeking aspect. So immediately you're now in the game of artificial intelligence that becomes curious and scientific in exactly the sense that we were talking about. And this is going to be particularly important in terms, say, of autonomous vehicle research. So what you're going to be looking for is an application of active inference in such a way that an autonomous vehicle will know where to look next to resolve its uncertainty about the situation in which it finds itself. And furthermore, will have an intentional aspect in the sense that it's rolling out into the future to select in the moment, dependent upon its current beliefs about the state of affairs in the world, what is the most likely thing it will do given the kind of thing it is. So one simple example, it will say you're designing AI for a self-driving car, and you are now trying to think about how will you design this to be truly to show the kind of sentient behavior that I would expect an experienced human driver to show. And you present it with a problem that a child is running into the road, but there's a family of 5 in the car behind you. So now what do you do? Do you do an emergency stop and potentially risk the car behind you crashing into you? Do you swerve? Do you knock over the child? So all of these things require, first of all, an understanding of the current situation. So you have to actually search for visual information about, whether there is a child running into the world and what's the likelihood of that happening. You've also got to look in your mirror to work out, what resolve uncertainty about the occupants of the car behind you. And furthermore, you have to have a number of policies, available or allowable policies, that are going to be informed by the prior expectations about the kind of driver you are, the kind of person you are in this particular instance. And I presented you with an impossible ethical problem about what to do, but you have to be able to write that down, and you have to be able to express it in terms of how surprising would it be to find yourself in charge of a vehicle that caused these devastating consequences of one kind or another kind, and then you just pick the one. But to do that properly, you've got to have an intelligence that is beyond current large language models and current AI, that is curious about the situation in which it finds itself. And then, furthermore, it has to have a world model, exactly as you say. So the world model is the generative model, and this is the kind of thing that people like Jan LeCun currently. A lot of the people are now, a lot of the thought leaders in industry are now sort of wandering away from large language models, and they're setting up their own labs, predicated on the notion that we need intelligence that is, if it's going to be truly aligned with us and part of our ecosystem, then it has to have a generative model or a world model that includes us in it. And furthermore, it has to share the same kind of common ground we were talking about before, which means it has the same values and the same. And what are the values? Well, they're literally those prior preferences. The probability of an outcome given the kind of thing that it is. And if it's like me, then it will have the same kinds of preferences for not inducing these kinds of surprises or other kinds of surprises. So that would be one example of how you would look at the next generation of artificial intelligence through the lens of active inference. And I'm not pretending that I'm doing that. I have friends that are trying to do it, but this is at this stage rather aspirational.
Thank you.
All right, thank you. We do have one last question in the Q&A, and then I'll hand it to Barbara to pull in any other questions or anything else. It's back to Rob, and Rob asked, I think I may have noticed the wave function in one of your equations, and I'm curious how the wave function may relate to Markov blankets.
So the That's an easy one to end with, isn't it? But it's not going to make sense to anybody unless they've done quantum mechanics. The wave function is simply the solution of that Fokker-Planck equation when the Markov blanket is written down as a Schrödinger potential.
Right.
Okay, well,
Thank you.
Oh, I should just add the trick to get it into quantum mechanics is that instead of working with that probability distribution that I was associating with the generative model or the probability of finding me in a particular state, you work with the complex root of it. And then you work with probability amplitudes, but the maths is exactly the same. So I should just qualify that.
well, Carl, unfortunately, I think you're going to have to come back again because I've never seen such an active chat. Do you have a couple more minutes before you have
Yes,
to
of
go?
course.
Okay, well, um, we are joined today in the audience and we're by Dr. Jay Bloom, who has been very active in the chat. And Jabe, I'd like you to join us for a second if you're still here. There he is. You wrote a couple of things, that sort of tie what Carl is talking about to the language that we use around complexity in organizations. And I was wondering if you could expand on that a little bit for him right now in terms of the balance between stability and change and contingency.
Yeah. So I was in the chat. I put a couple things. Wow, it's really raining out there. I hope you can hear me over the sound of the rain. Some of the things I was observing were so Cillier had this idea that reminded me a lot of your Markov blankets, which is in order for something to be a self-identifiable thing, it has to essentially move slower than the environment that it's in. So it has to have certain kinds of commitments that differentiate it from the environment, right? So it's very similar to the Markov thing that you're pointing at. I think there's some sort of stable center that's still interacting with a fluid or moving environment. So I put a quote in there that he uses to kind of describe that. So I thought that might be interesting to look at. But also from kind of an organizational perspective, Herbert Simon has this way of describing how information moves in an organization. He basically says imagine that you're in a building and there's an air conditioner in one room. Information kind of is that particular room getting colder. So that's your difference, right? But when you open the door, every time you open the door, a little bit of the cold air gets out. So he basically is describing the way in which for information to move in an organization, it almost always diffuses or homogenizes in a way. It can't actually stay stable. Or somehow when you, in your language, maybe when information moves into a larger Markov blanket, it has to blur a little bit or become less sharp or less clear in his language or in his way of thinking about it. So in his information theoretic, right, information kind of blurs out as it moves across organizations. And the way he kind of, I think, describes this is when you want to move information from a small team to a larger team, there has to be an activity of structuring the information in a way that it can move across the boundaries, allowing the internal and the external to remain separate in essence. So I can emit little bits of data out of my group, but if I try to bring someone in to what we experienced, it will almost always, the information will kind of collapse. And so it's really easy for most people who do information generation inside of an organization. If you go into a room with a group of people and you brainstorm up a brand new way of I don't know, building bricks, and you bring someone in from the outside and you try to explain how you arrived there, you almost never can get it to happen. People just, they didn't follow every step along. People can't remember how they actually got to the conclusion that they're at. They only know that they kind of stabilized. Well, the other way of kind of saying it is when you're playing with sticky notes on a board, there's a sense at which, oh, we have enough stickies now, and the room will coalesce around an answer. But how you arrived at the answer is very difficult to explain. And if you bring someone else into the room and have them look at the same set of stickies, they'd just be like, there's random stickies on the board. Like, that doesn't mean anything. So there's this, like, for Simon in this version of it, I think there's this idea that, like, yeah. So I guess what I'm interested in, if I could hear you talk about it, because I was actually talking to Alicia Shararo about something very similar this morning, is like, how would you explain, or how do you think about how things continue to differentiate without homogenizing? Like, how do these things balance off of each other, in essence? Like, every time you differentiate something, and then you try to, like, integrate it into larger things, you get this kind of diffusion effect or this homogenization effect. So how do you think about that? And then the only last one I was going to point out, the only last kind of thing that your thinking kind of reminded me a lot of, was kind of Vimstat's idea of levels of organization. So basically, he has this idea similar to, like, you had this line you're going across, and you're saying, like, we live in this kind of, like, specific space. And for Vimstat, he basically has this thing. He says, like, in essence, the ontologies and temporalities of certain things indicate their epistemologies. So, for instance, like, the size of things that are in quantum physics and the time periods in which those things exist allow you to know about them in certain kind of ways. And same thing with ants and planets, because they're just, like, on different time scales, and you can only pay attention to certain things because of the type of beings that humans are. So he kind of talks about it as being like, we're resonating with different timescales and different objects, and that's the only thing we can know about them, is the way that we resonate. So for him, like, your different scales that you were pointing out have to do with, like, the kind of beings that we are, the way that we can know about those things automatically produce certain types of understanding or epistemological structures that are kind of associated with them. So I just thought that was an interesting one for you maybe to play with as well. Anyway, I don't know if I have a question, but those were the things that I was pondering in the chat. If that makes any sense.
Well, yes, thank you. I mean, that the second point you made, yeah, that's exactly what I was trying to get at. And I would concur exactly. We only have a limited latitude of scales that we can actually resonate with, and just the fact that we exist at a particular scale gives us a certain relational, certain perspective on those scales. It sort of remind me almost of Carl Friston's relational quantum mechanics. You've got to think about not just the the observer, but the observed. And certainly if you're watching an observer observing, then the observer of the observer is, and all of these things have to be at the right scale before they can talk to each other. Absolutely. That seems very sensible. I also like your sort of, I thought you were going to talk about satisficing. So, which is extremely close conceptually and certainly in narrative form to this sort of Bayes optimality under priors that make you basically Bayes optimally optimistic and also coarse-grained. And I think that coarse-graining aspect is exactly what is would be the response to the things that you were describing. So this diffusion of information up the hierarchy or to the outside. It sounds to me very, very much like the application of the renormalization group to world models, where you're compressing and coarse graining. And I think that that's a really important aspect. It's not something we talked about, unfortunately, but very briefly, you can actually approach the variational free energy not from the point of view of Richard Feynman and the thermodynamics, but you can take the Russian route, which would be via things like Kolmogorov complexity through to Soloviev induction and through to universal computation. The key theme here is compression. If you can compress it, if you can summarize it in your 1 page or your 100-word executive, you've got the essence of what's going on. So you can get those thousands of sort of sticky notes together into something that you all recognize as a coherent thing. That's, I think, a really powerful way of maximizing the marginal likelihood or maximizing the average marginal likelihood, which turns out to be a mutual information. And that you can always read that as the right kind of compression. Of course, you have to be very skilled in the way you compress things, but it's compression at the end of the day. And that, of course, is just the minimization, the complexity. It's, using as few degrees of freedom as you can in order to provide an accurate account of, your juxtaposed levels, be they below or be they above you.
Yeah, I usually have this like way of describing that as like you kind of dehydrate the information so it can rehydrate in a different context. So like it's actually that you have to create a structure that will be useful in a different context, but increases the probability that certain things will occur in that other context as well, right? So it's because you usually can't just take the information or structures right out of one context and put them into another. You have to like strip away the specifics of that particular context. It's kind of the dehydrating aspect of it, and make them stable together, and then move them into another context, and then let them rehydrate or reform in that other context. But if you do that well, what you're doing is increasing the probability in that other context that something beneficial will occur in that other context. So I think of it kind of like seeds sometimes, right? Like the beauty of a seed is like the absolute minimum structure you need
Yes.
to like move a plant from one place to another. And that's kind of what you're looking for, as a way to like make information into just seeds that can be transplanted into a different type of soil or something like that. I think that's because it's not just up, right? It's not just that I want to go up. I actually need to go back down again into another context often, right? I need to take it from one team up to an organizational level, and then I need to plant it back in another team. Yes. And have it like blah. And interestingly, for a lot of like process people who deal with process, agile coaches and stuff like that, being very, very rigid about the rules, like this is exactly how you do this process, actually tends to break things, right? So it's actually, you have to be able to like figure out the right way to explain or narrativize the thing so that people have the opportunity to practice it a little bit and then like evolve it as their own version of the process, but while still achieving similar or beneficial outcomes. Anyway, I think it's just interesting to try to figure out how that function works, because again, I recognize in your kind of Markov blankets this idea that he has about like structuring information and making it solid, and then I still want to know how things move around. Dave Snowden has a very kind of similar way of kind of thinking about some of these things, where he kind of says, when you move information around, he likes the idea of like mems, or another version of this. It's not my favorite version of it, but it's the same thing. Like, how do you like compress something now really, really, really tiny so it can move around and have the same meaning in many, many places, or similar meanings in many places? Anyway, I don't know. I thought it was fascinating. I really loved your talk. Thank you.
I just love that. Just one little observation. Your description of moving it around is almost isomorphic with the way that theoreticians understand sleep. So if you take all your experiences today and you want to move them to tomorrow to do good, you've got to compress them and forget about all the rubbish and do your house cleaning and minimize that complexity when you're asleep. Or at least introspectively.
We need organizations to learn to dream better. I like it.
Yeah.
It could be dangerous. All right.
Oh, I have one more thing. Just one more question. I kept on coming to the thought in my head was some of what you were describing. You use the word inference a lot, but in my brain, it's abduction. Would you differentiate what you're saying from abduction, or is it I'm just using the same word for something, different word for the same thing?
That's to say, absolutely. So I sometimes use inference as the best explanation for certain kinds of philosophers. If I'm talking to some Bayesian logicians, it is just abductive inference. No, it's just exactly the same thing. Yeah.
Yeah. Because I think, again, so like my dissertation was all about temporality, human experience of time and stuff like that. And so to me, abduction is partly like that you have like a momentum or a life experience that's informing the next step. So it's never like whereas most logics can be like, I have almost no history to them. They just are like, I'm inferring this based on the information I currently have, blah. Abduction feels to me more like it is cumulative experiences. It's, guessing and things like this, and learning, which is another term you kind of used. So I was just wondering if that was the same. So I'm glad I wasn't too far off.
You were spot on.
Oh, thank you, Jade. That was great. Well, if we did not get to your question or we missed it, we're really sorry. Carl, I wasn't kidding. I think you're going to have to come back because I've never seen such an active chat. And the questions were great. And thanks to all of you for participating in this. Carl, thank you so much. Oh, before we go, if they want to follow up on your work, do you have an academia page? Do you have a website? Where should they look for you?
Now I'm trying to be a recluse, so you won't find me on social media or websites. There is something called the Active Inference Institute you can find
There you
on, but they're very American and very Californian, so that'll be great for half of your audience.
Well, yeah, you do. Your LinkedIn page is quite sparse. I was like,
I
is
didn't
this the
know I
right
had
Carl
one.
Friston? You do. Well,
Oh,
anyway, Carl, thank you so much. Please come back again. You're welcome anytime. This was great. If you, for those of you in the audience, thanks again for coming by and joining in on the conversation. You can find Carl's work at the Active Inference Institute. And have a wonderful day, and thank you so much. Bye, everyone.